This topic is one-dimensional unconstrained optimization. So we are going to start the optimization topic. So before this topic, we have finished the topic of the linear algebra, finding the solution of linear system of linear equations using numerical methods. And before that, we finished the topic of finding the roots of nonlinear equations, and we started with the approximations and error calculations. So this is actually the fourth main topic, optimization. After that, there will be an topic of curve fitting and interpolation. Then there will be the topic of numerical integration. And then after that, the last main topic will be the numerical solution of the ordinary differential equations. So in this topic, there will be also 3 chapters. So first chapter is this chapter number 13. Then we will cover some part of the chapter number 14, and then we will cover chapter number 15. So chapter number 13, this is the one-dimensional unconstrained optimization. In the chapter number 14, it will be the multi-dimensional unconstrained optimization. And whereas in chapter 15, we will look at the constrained optimization, where we will look at the linear programming part. So it will be a series of 3 chapters. So today we are going to start from chapter number 13, one-dimensional unconstrained optimization. So this is the simplest of the case in the optimization problem. And remember that in the optimization, so can you hear me, and can you also see this slide? Just want to confirm.
Yes.
Okay. So if you remember, so just remember that in the optimization, you have to either find the maximum or a minimum of a function. So if you have a function f of x, and that function is one-dimensional. One-dimensional means that is a function just represented in one independent variable. So that function's value will increase or decrease with x, okay? So sometimes this value will be increasing and it will go to some higher value, and then from that higher value, this value will start decreasing. So that highest value will be the maximum of that function. But that maximum of that function can be a local maximum, or it can be a global maximum, as you can see in this figure 1.3. So suppose if we have a function whose graph is something like this. So here in this case, this function is showing 1, 2, 3, 4 extreme points, okay? That means, so between this first area, so this point is the global maximum. That means there is no other point. There is no other point within the domain of this function that is higher in value than this point. And similarly, this is the global minimum point. There is no other point on this function in this function's domain where the value of this function is lower than this point. But there can also be the local maximum and local minimum. So the local maximum and local minimum will be within the range of certain points in the domain of the function. The value will be either maximum or minimum. So therefore, when we are talking about the optimization of the function, so we should be clear that whether we are referring to the global maximum minimum or local maximum or minimum. Okay, so many of the functions are like multimodal functions. So in those multimodal functions, that means there can be both local and global optima, that is the local and global maximum and minimum points will exist. So in almost all cases, we are interested in finding the absolute highest or lowest value of a function. Okay. So then how we can find the absolute lowest and highest value of the function? In this case, we will consider three methods. Okay. The first method will be called as the golden search method. Okay. So, but let's see how do we distinguish global optimum from the local one. Okay. So yeah, sometimes it is not that easy to distinguish the global optimum and from the local one. But certain techniques can help us out. So for example, by graphing to gain insight into the behavior of the function. So the graph will give us some of the uh, uh, pic, uh, pictorial uh, way to find out the global optimum point. Then using randomly generated starting guesses and picking the largest of the optima as the global. Okay, so this probably we will do in the next chapter. Okay, and then perturbing the starting point to see if the routine returns a better point or the same local minimum. So with this approach, we can also try to guess whether it is a global maximum or a local maximum or global minimum or the local minimum. Okay, so as I have told that certain methods we will discuss. So first of that method is the golden section search, golden section search. The second method will be the parabolic interpolation, and the third method will be the Newton's method. Okay, so for finding either the maximum or minimum of a function uh, in uh, in algebra or in calculus, what we do is we normally find the first derivative of the function. We equate the first derivative of the function to 0 and then find the root of that function. That means we find the root of the first derivative of the function, and that root will give us the either the maximum or minimum of that function. Whether it is a maximum or minimum, it depends on the sign of the second derivative. Okay, for that value of x for which the derivative of f of the function of x was 0. If the sign of the second derivative was negative, then that function will be that value of x will be a maximum. If the value of the second derivative is positive, then the value of x for which we have found f prime of x is equal to 0 is a minimum. However, in this golden section search method, it is a numerical method, and it is in this method a unimodal function has a single maximum or minimum in a given interval. So it's the requirement for this section, this method is that we will identify an interval, and within that interval there will be a single maximum or minimum value. Okay, so that single maximum or minimum value we will need to find, and the corresponding value of the independent variable we need to also find. So this is called a unimodal function. So in that means the steps are: first pick 2 points that will bracket your extremum, that is xl, xu. So the xl and xu are the extreme values, outermost values. Okay, and then we will pick these two values. Then we will pick an additional third point within this interval to determine whether a maximum occurred. That means another point will be picked within this xl and xu. So there will be another point. Okay, maybe we can call that point as x1 or x2. Okay, but how uh, we will determine whether there is a maximum occurred or not, so that we will see in this method. So then we will pick a fourth point. Not only the third point, we will also have a pick a fourth point within this interval, xn and xu, and to determine whether the maximum occurred in the first three interval or the last 3 points. So because now we have 4 points, initially XL and XU are the 2 points, and then we pick 2 more points. So then there will be first 3 points and the last 3 points. So for example, if the points are 1, 2, 3, 4, so the first 3 points are 1, 2, and 3, and the last 3 points are 2, 3, and 4. So the maximum can occur either in the first 3 points or in the last 3 points in this case. So we will determine the uh, interval in such a way. Okay. So in this method, pick an additional third point within this interval to determine whether a maximum or whether a maximum occurs. So to ensure whether the to ensure that the maximum or in another case the minimum occurs in the first third 3 points or the last 3 points, we will follow a certain procedure, this uh, which will give rise to the uh, emergence of the golden ratio. Okay. So the key is the key is making this approach efficient by choosing intermediate points wisely, thus minimizing the function evaluations by replacing the old values with the new ones. So in fact, when we will first pick the 1 point and then we pick the second point, in total we have 4 points. So this type of picking of the points will give us the first iteration, and then we will iterate it for the second time, for the third time, for the fourth time. But for each iteration, we have to make some modifications in the values of the x. And here, these modifications in the values of the x have to be performed by following certain rules. And then following that rules, we will try to perform as few calculations as possible. Okay, so this is how the whole picture comes into. Uh, for example, if we have this function of x, and this function has a maximum value at this point, and its extreme points are xl and xu. So the distance between xl and xu, that is xu minus xl, is represented by L naught. Okay. And within this distance, xl and xu, we will choose 2 points, x1. Okay, so I think it is not shown over here, but we will choose 2 points. So x1 will be here, x1 will be here, and x2 will be here. Remember that x2 will be on the left side of x1, and we will choose x1 will be here. Okay, so x1 will be at a distance of L1 from xl, and x2 will be at a distance of L2 from xu. Okay, so sorry, yeah, L2, it will be at a distance of L2 from xl, and which is the same distance as point x1 from xu. So you can see that we will, so that is in the second iteration, sorry. I think it would be better if I show a point x1, x2. So this will be x2. It's difficult to type here. And this will be x1. Okay. Yeah, x1. Okay. X1 and x2. So x1 will be this side, on x2 will be on that side, okay? And these points will be chosen in such a way that, of course, you can see that L1 plus L2 will be equal to L0. So L1 is this distance, L1 is this distance, and L2 is the distance on the other side. So L1 plus L0 is equal to L0. And then L1 over L0 divided by L2 over L1. So this means that the second ratio is that the second ratio condition says that the ratio of the length must be equal. Okay, so the points will be chosen such that the ratio of this L1 with L0 will be the same as the ratio of the L2 with L0. Okay, as the ratio of L2 with L1. L1 to L0 is the same as L2 over L1. Okay, so now we will have these two conditions, and then if we solve these two conditions and then represent L2 by L1, L2 over L1 by R, and then we will solve this equation for R. That means if we can represent L2 over L1 by R, then we can represent this whole equation by into R, and then if we will solve the value of R, we will get a ratio which is called as the golden ratio, okay, 0.61803, which is equal to square root of 5 minus 1 divided by 2. This is called a golden ratio from a very long time, and it has a very interesting property that if you take the reciprocal of this ratio, then the reciprocal of this ratio will be equal to just can be obtained by the addition of 1. As you can see that the reciprocal of this golden ratio is equal to the ratio itself plus 1. Okay, so this is the only number in which if we just add 1 to that number, and then that will be equal to the ratio reciprocal of that number. Okay, so this is called as the golden ratio. So you can see that the value is 0.61803. That is using this golden ratio, we can divide an interval into approximately 62% and 38% ratios. So 62% and 38% ratios. So this may be this is useful in this optimization problem. Okay. So for the wise choice of the interior points, so that means we have to choose the points x1, which is here, and x2, which is here, in such a way that this point x1 will be at a distance of x, at a distance of d from xl, and where d is the d is the distance determined by the golden ratio multiplied by that interval. And similarly, x2 is a point which is a distance d from the xu, that is xu minus d. Okay. Okay, so and then similarly for the other case. So one is for the increasing case, for the other is for the decreasing case. But in any case, x2 is always on the left hand side of x1. Okay, x2 is always on the left hand side of x1. Okay, so let's see. There are two rules. So the method starts with the two initial guesses xl and xu. That bracket one local extremum. So the next two interior points x1 and x2 are chosen according to the golden ratio. So we start from xl and xu. So we have a function. So we will take 2 points on that function. Okay, one is the leftmost point, the other is the rightmost point, xl and xu. Okay, but additionally we have to take 2 more points between these points. Between these xl and xu. But these 2 points x1 and x2 have to be taken in such a way that we will take the golden ratio. Okay, so first of all, the golden ratio is under root 5 minus 1 divided by 2. Then that will be multiplied by, so this ratio, which we know that the value is 0.618, that will be multiplied by the interval difference between xu and xl. And then from here, x1 will be given by xl plus d, okay? And x2 will be given by xu minus d. So hence, here we note that because d is about 0.61%, okay? So therefore, uh, x1 will be on the right hand side, x2 will be on the left hand side of xu, okay? So, so we will have points x1, x2, sorry, xl, x2, x1, and xu in that range from left to right, okay? So x1 and x2. So, so we will determine x1 and xu. So then the function is evaluated at these two interior points. So we find the values of the function at x1 and x2, okay? So once we determine x1 and x2, so we will find the value of the functions at x1 and x2, fx1 and fx2. So now we will have these values. So now there are two rules, okay? If the value of the function of x1 will be greater than fx2, so then the domain of x to the left of x2 from x1 to x2 can be eliminated because it does not contain the maximum. And then x2 becomes the new xl for the next round. Okay, so then maybe we can see it from here, from this figure. So from this figure, okay? So suppose here we can see that we have this value as x1, fx1, and this value as fx, sorry, the left-hand side is value, this is fx2, and this value is fx1. So here you can see that the function is increasing from x2 to x1, okay? So the value of, that's why the value of fx1 is greater than fx2. So this means that the function is increasing from x2 to x1. If the function is increasing from x2 to x1, so for the second trial, our value of xl will become equal to the value of x2. That means this area will be eliminated for our next trial, okay? Because the function, the value of the function was increasing, and then this will also give us the idea that the maximum of the function will be found out towards the right side of this section. On the other hand, if it is opposite, then the area on the right hand side of x1 will be eliminated, okay? So that means if fx2 is greater than fx1, then the domain of x to the right of x1 from xl to x2 would have been eliminated. Okay, so in this case, x1 becomes the new xu for the next round. Okay, so in this way, we will determine it. So now new xl is determined as follows, and using the golden ratio, and then plus adding with XL. And the bottom line of the golden section search is, so this method is called as the golden section search. So the benefits of golden section search is that if you know there is a single option in an interval, it will always work. Okay, so this method always works if there is a single option, that is it, if there is a single maximum or minimum value. And it allows an exact upper bound estimate of the error. And also it minimizes the function evaluations. That is, you do not need to recalculate all the function values for the next iterations. So it is numerically efficient. That means many of the values of the functions which we previously have calculated can be reused. Okay, so this was some brief theory about the golden section search. As always, it is better to do the example to understand this process. Okay, so suppose if we have a function 2 sine x minus x square over 10, and we want to find the maximum of this function between 0 and 4. That means the extreme values of 0 and 4. Then using the golden search section method, how we can find it. So as a first step, we will find the value of d. That is the distance of the points x2 and x1 from xu and xl respectively. Okay, so the d is found as, you can always find d by multiplying the interval xu minus xl with the golden ratio. Okay, so golden ratio is always is a constant, under root 5 minus 1 divided by 2, and then the interval is 4 minus 2, so it will be 2.472. So this 2.472 will be the distance of points x1 and x2 from xl and xu. So after we determine d, then we will determine the point x1. So point x1 will be equal to xl plus d, and point x2 will be equal to xu minus d. So here you can see that xl is greater than x2. So it means that x1 will occur towards the right of x2. Okay, this will always happen. This is because of the use of this golden ratio. Okay, so after we determine x1 and x2, so we will find the value of the function at x1 and x2. That means if we input x is equal to 2.472 into this function, and then we will find the value of the function. Similarly, for the value of x2, we will put the value of 1.528 into this function, then we will find the value of x2. So we will determine the values of fx2 and fx1. So now you can see that the value of of the function at x2, fx2 is 1.765. Value of the function f fx1 is 0.63. So now you can see that the second condition is meeting in this case, because fx2 is greater than fx1. So because fx2 is greater than fx1, so it shows that the value of the function is decreasing from x2 to x1. Okay, so since the value of the function is decreasing from x2 to x1, the maximum is in the interval defined by xl, x2, and x1. Okay, because the value is decreasing from x2 to x1. X1. So that means x2 the value is higher, x2 1 is value is lower. So it means that the maximum is somewhere behind, because we are taking the unimodal function. So function is either increasing or decreasing. Okay, so therefore in this case, for the new interval, the lower bound remains xl is equal to 0, and x1 becomes the upper bound. That is x1 will become 2.472. So in addition, the former x2 value becomes the new x1. The former x2 value becomes the new x1. That is x1 is equal to 1.528. So further, we do not have to recalculate fx1 because it was determined on the previous iteration, and it is 1.765. Okay, so for the next iteration, then we will have these two bound values. 2.472 minus 0 is equal to 1.528. So that means in this case, because when x2 was greater than x1, then we have taken, then we have eliminated all the portion from x1 to xu. Okay, so x1 has become xu in this case. So x1 has become xu. So it will be 2.472 minus 0 is equal to 1.528, and x2 will be then 2.472 minus this value, and x2 will be in this case 1.531. So in this case, 1.531 is the value which is less than the function at the value at x1. So the maximum is in the interval defined by x2, x1, and xu. Because in this case, you can see that now the value is 1.531, which is the value at x2. And we will compare it with the value at x1. The value of x1 is in this case 0. Okay, x1 is in this case 0, and then that value was 0. Okay, so the value has increased from 0 to 1.531. So that means it is inside of this interval x2, x1, and xu. And then the process can be repeated until the results are tabulated as below. So in this case, you can see that can do the iterations, and then we can see that the value is converging at this value 1.7755. Okay, and then the value is converging it. So perhaps as always, it will be better if we do it on Microsoft Excel. Okay, so let me do it on Microsoft Excel. Okay. So first of all, what was the function which we are evaluating? So we are evaluating this function. Okay. We want to find the values of this function, the maximum or minimum values of this function. So we are evaluating this function. Can you see this Microsoft Excel on the screen?
Yes.
Okay. So we will start from the column I, which is for the iteration. And then we will start from XL, and then XU, okay? Then X1, and then X2. But I think for finding the X1 and X2, we need to find the value of D as well. Okay, so this is how the process goes. So I, that is the first iteration, and XL and XU are given. That means we have to find the maximum or minimum between these values. So 0 and 4. Okay, so it is XL is 0, XU is 4. And what is the f of XL? So this is the column for f of XL. And then here f of XU. Okay, and here we will need to find the D. And what is this? This is f of X1. And then f of X2. Okay. So from XL, we have to find the f of XL. So for this, we need to input the value. So the function is 2 times sine of x, so which is 0. This is this value, minus x square, this value, divided by 2. So which is equal to 0. Okay. Yes, 2 sine b8 minus b8 square divided by 10. Yeah, I think I need to divide by 10. Divided by 10. So it is 0. So now, since now I have set up this value for this x naught, I can copy this value because over here. So this will be the value at fxu. Okay, and then control V and then control V. Okay. But now what is D? The value of D is equal to the golden ratio. Okay, the golden ratio. Okay. So what is the golden ratio? So golden ratio is okay. So the golden ratio is square root of 5 minus 1 divided by 2. That is the golden ratio. Yeah, square root of 5 minus 1 divided by 2. Okay. So we'll use this golden ratio. Okay, so and then this golden x1 and x2 are, what are those values, x1 and x2? Yes. Yeah, from here. So we will find the value of D. So value of D will be equal to it will be equal to SQRT 5 minus 1 divided by 2, right? It is 0.618. So this should be multiplied by XU. This is XU minus XL. So it is 2.472. And what is X1? So you can see that X1 is equal to XL plus D. Okay. And what is X2? X2 is equal to XU minus D. So we will find XL. XL is equal to XL plus, sorry, X1 is equal to XL plus D. And so therefore, since as I found the value of X1, the corresponding value of the function fx1 was found. And now X2 is equal to which value? This value minus D. Is it correct?
Yes.
No. X2 is equal to XU minus D. Okay. So x1 is equal to XL plus D, x2 is equal to XU minus D. Okay, so you have to be very careful. So we have completed this first iteration. Okay, and in this first, after this first iteration, we have found out the values of these functions of x1 and x2. So now here we can see that this interval now, this interval D is quite large. Okay, so by successive iterations, we have to narrow down this interval. So once we can narrow down this interval to some sufficient value, then we can find the corresponding values of fx1 and fx2, which will be quite close to each other. Okay, and then that at that point we will almost get the optimum value. Okay, so for the next iteration now, that will be the iteration number 2. So it will be equal to the first iteration plus 1. Okay, so it will be the second iteration. So then, so now I think now we have to put some if statement over here. So according to the rules, so for example here, yeah, if fx1 is greater than fx2, then this value will be x2, or if fx2 is greater than fx2, then this value will be x1. Okay, so now we will have to apply this rule. So what is the rule? The rule is if fx1 is greater than fx2, okay, so then this value of fxl will be what? So it will be, because if fx1 is greater than fx2, so that then that means the interval is in the so for example, fx1 is here, fx2 is here, fx1 is greater, so that means the interval is increasing. Okay, so then that means we can eliminate the first interval from xl to x2. So it means that now our xl will become equal to x2. Okay, so this means that if fx1 is greater than fx2, so then this value will become equal to x2. Okay, if not, then this value will remain the same. Okay, so this is the condition. And for this fx2, it is equal to, we need to put another statement. Okay, for this we need to put the another statement. Okay, if fx2 is greater than fx1, okay, if fx2 is greater than fx1, so that means fx2 is located here, fx1 is located here. So if, for example, if this is, so okay, let me see, if this is the fx2 and then this is fx1. Okay, so here I have shown fx2 is greater than fx1. If fx2 is greater than fx1, then that means the function is decreasing from fx2 to fx1. So it means that we can our maximum of the function is located into this section. Okay, so then that means from x1 to xu we can eliminate it. Okay, so in this case, let me see, if fx2 is greater than fx1, then then our starting value will become the that means our fx2, then our fxu, that means this fxu will be the value that is fx, this value fx2. Okay, or no, sorry, fx1, this value. Okay, this value will become our fxu. Otherwise, the value of xu will remain like this. Okay, so this is a little bit tricky, but I think this is how the logic will work. So anyway, so then I will copy this value, and then I will copy this value, and then the value of D will be now found out, and then other values now can be calculated. Okay, so I have calculated it before in over here. So it was like this 2.472, 0.63, yeah, and 2.472, 0.63, and 1.52. Yeah, 1.52 it was before. Okay, so in this way we have set up this sheet, and then I can expand this value, and now I can make as many iterations as I want. Okay, so that you can see that by each iteration I am narrowing down on the values of D, and then here I can see that the values of the x1 and x2 are coming closer and closer to each other. Okay, and the values of x1 1.775, 1.775 is getting closer to each other. So I don't know where to stop, but I think one of the way for stopping is that we can take the average of this. We can take the average of these x1 and x2 values. So it will be x1 plus x2 divided by 2. So we can take the average, and then for f max, we can take the value of the function at the average value. So that is equal to what? That is equal to, for example, I take this control C and then control V, and then just copy it down. And I can see that now the value of the function is, you see, 1.775, 1.775, the value is approaching that function, okay? And if we can find the error, absolute percentage error, so it is equal to ABS, absolute percentage error in the average value. So it is this one minus this previous value divided by the current value divided by this current value multiplied by 100. So it is 61. Yeah, we start from the absolute error of 61, and then maybe, yeah. So the absolute value is now 0.02. So it's quite low, absolute value, okay? So here you can see that we can see that our approximate answers after 18 iterations are 1.4272 and 1.775, okay? So we can verify these answers as well. So for example, if we use this solver function, data solver. So let's copy this function. Let's take this value of x and f of x. Okay, so the value of x is say 0, and then f of x is maybe just we can calculate. So here I have calculated this value of x. So if I apply the data and then solver, and then if this solver function, what I want to do is I want to use this value of this function to maximize it, okay? I have selected it, and then I have set the objective to maximum by changing the value of this value function, and then solve it and converge to the values, and then it had found the solution. So here you can see that uh, the value of the value of x is 1.427552, and then what we have found over here is 1.775726. Okay, yeah, so it's quite close actually. Okay, yeah, sorry, 1.427232, 1.74275552. Maybe if we can take some more iterations, okay, then we can get the more closer values. So you can see that now we're getting like 1.42755, 1.427552. Yeah, so very close values, and the maximum value of the function we have got is 1.775276. So in this way we can simulate it on we can set it up this problem on Excel. Okay, so the most important point is to set up these values of the XL and XU using these two rules. Okay, if fx1 is greater than fx2, then what is the rule? If fx2 is greater than fx2, then what is the rule? And in qualitative terms, as I have told that, so for example, if this is fx2, okay, and if fx1 is here, okay, fx1 is here, fx1 is here. So here in this case, fx1 is over, fx2 is under, okay? X2 is on towards the left of x1, okay? But fx1 is greater than fx2, it means that the function is increasing from x2 to x1. So this type of formulation gives us the indication that the function is increasing from x2 to x1. So therefore the maximum will occur towards the right of x1 in this case. So we will take the interval x2, x1, and xl for our case. And then anything towards the left from xl to x2 will be eliminated. So in that case, for the next interval, xl will become equal to x2. So that's why we have put this condition, okay? So yeah, so for when the condition is right, so it will be x2 over here, okay? So that was the case. Do you have any question regarding this?
No.
No.
So yeah, so I hope it is you can understand it well. So and then you can try to do it on Microsoft Excel, and then it will be easier for you to imagine it. All right, so that's all for